Hello! In this video, we are going to prove the following theorem. Let x and y be real numbers. Then, for all natural numbers n, x to the power of n plus 1 minus y to the power of n plus 1 is equal to x minus y times the sum from k equals 0 to n of x to the power of n minus k times y to the power of k. Okay, so now let's get into the proof. To start out the proof, let's give ourselves two real numbers x and y. And from here, we want to prove that for all natural numbers n, this is true. And since we're trying to prove a statement about all natural numbers, let's use induction. And so let's start with the base case. Now in the base case, we're trying to prove that this is true in the case where n is the smallest natural number. And for us, we'll say it's 0. Which means we want to prove that x to the power of 1 minus y to the power of 1 is equal to x minus y times the sum from k equals 0 to 0 of x to the power of 0 minus k times y to the power of k. So to prove that, let's just write out the right-hand side. Now, since the lower and upper bound of the sum are the same, we know that the entire sum is just going to be equal to what we have here with k replaced with 0. And we know that x to the power of 0 is 1, y to the power of 0 is 1, so this entire thing is just x minus y. And of course, this is the same thing as x to the power of 0 plus 1 minus y to the power of 0 plus 1. So we have shown that this is equal to this. In other words, we have shown that this is true in the case where n is equal to 0. So this completes the base case. Now let's move on to the induction step. Now in the induction step, we give ourselves an arbitrary natural number n where this is true. The whole goal now is to show that this is also true for n plus 1, which means we want to show that x to the power of n plus 2 minus y to the power of n plus 2 is equal to x minus y times the sum from k equals 0 to n plus 1 of x to the power of n plus 1 minus k times y to the power of k. So to do that, let me start out by writing the right-hand side, where we replace wherever we see an n with n plus 1. Now to start, since n plus 1 is strictly greater than 0, we can pull away the n plus 1th term from the sum, and write it as the sum from k equals 0 to n of this, plus exactly this, where we replace k with n plus 1. So really, this sum is equivalent to this. The next thing we are going to do is we can use our properties of exponents to rewrite x to the power of n plus 1 minus k as x times x to the power of n minus k. And as for our leftovers over here, well, this is just x to the power of 0 times y to the power of n plus 1. Well, we know that x to the power of 0 is just 1, so we have 1 times y to the power of n plus 1, which is just y to the power of n plus 1. Now, if you recall, one of our rules from summation is that we can pull the x to the outside of our summation. Right, we could do this because x doesn't depend on our index k. And now that we've done that, let's distribute the x minus y across this parentheses to these two terms. Now, take a look at our first term. Ignoring the x, this is precisely what we have in our induction hypothesis, right? We know that this is equal to x to the power of n plus 1 minus y to the power of n plus 1. Next, let's distribute the x across this parentheses. And let's distribute the y to the n plus 1 across this parentheses. As we can see, the two middle terms cancel out, and we are left with this. So as you can see, we have shown that this is equal to this. In other words, we have shown that this is true, where instead of n, we have n plus 1. And that was the whole goal of the induction step, so this completes the induction step. And since we've completed both the base case and the induction step, this closes the induction, which means we have shown that for all natural numbers n, this is true. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.